So being able to determine the number of valence electrons is based on the quantum mechanical model, because the quantum mechanical model gives us the energy levels and the subshells of atoms. Since elements in the same column have the same number of valence electrons, they show similar properties. And since the number of valence electrons increases across a period, which is a row, the properties vary in a regular fashion. So we can use quantum mechanics to explain the properties of elements in the periodic table. Now, as I've mentioned earlier, the noble gas electron configuration is very stable. Except for helium, the noble gases have 8 valence electrons, and those 8 valence electrons give us a filled S and P subshell. This is very, very stable, and because of this, noble gases are not very reactive at all. Now this slide says everyone wants to be like a noble gas. I wouldn't say everyone. I'd say the elements that are close to the noble gases want to be like the noble gases. And what do I mean by close? I mean atomic numbers that are near. So let's look at alkali metals. If we look at the alkali metals, they are 1 electron higher than the nearest noble gas. So lithium has 1 more than helium, sodium 1 more than neon, potassium 1 more than argon, and so forth. And here are the valence electrons written out in their energy level and subshell. They're all in the they're all in the S subshell. They all have 1 valence electron, and their energy level is the same as the period that they're in. In chemical reactions, alkali metals want to lose this 1 electron, because when they lose 1 electron, they will have the same electron configuration as a noble gas, filled S&P subshell. Therefore, they'll lose 1 electron, they'll have a cation with a positive 1 charge. That is why the alkali metals always have a positive 1 charge. Now let's look at the opposite side of the periodic table, the halogens, which are 1 electron short of having a noble gas electron configuration. Fluorine has 9, neon has 10 electrons, chlorine 17, argon 18, etc. And here are the electron configuration of the valence electrons for the halogens. 1 electron away from having filled S&P. Now, nonmetals have options that metals do not have. They can gain electrons, and this is why the halogens, if they exist as an ion, always have a negative 1 charge. Because when they gain a negative 1 charge, they gain an extra electron, which gives them a noble gas configuration. Nonmetals also have the option of sharing electrons, which we'll see in the next chapter. And halogens will often share with other nonmetals, so they get the noble gas configuration. So nonmetals can gain electrons or share, but they're going to do either one to get 6 electrons in the P and 2 in the S. So a total of 8 valence electrons to be like the noble gas. So if we look at the 2 families that are closest to the noble gases, the alkali metals are by far the most reactive metals. They react with many other substances and do so very rapidly. In fact, in nature, there are no elemental alkali metals found. They only exist in the positive 1 cation state. And then the halogens are the most reactive group of the nonmetals. They're only 1 electron away from having a stable noble gas configuration. So the 2 families that are closest to the noble gases are the most reactive families in the whole periodic table. And if we look at the electron configuration of atom versus ion, we see that for elements that are within 3 electrons of the noble gas, of the nearest noble gas, they're going to lose or gain electrons to get a stable noble gas configuration. Now we've already talked about the alkali metals. They only have 1 electron extra. So they lose that electron, they have a positive 1 charge, and get a noble gas configuration. While the alkaline metals, alkaline earth metals, are 2 away from a noble gas configuration. If they lose 2 electrons to have a +2 charge, they also gain a noble gas configuration. So that is why the alkaline earth family always has a charge of +2. And like the alkali metals, the alkaline earth are relatively reactive, and no free elemental alkaline earth exists in nature. It only exists as the +2 cation. And aluminum, which is 3 electrons away from the noble gas configuration at 13 electrons, loses those 3 electrons to get the noble gas configuration of 10 electrons like neon. And let's look at these two nonmetals. We've talked about the halogens, how when they gain 1 electron, they'll get a noble gas configuration. But oxygen is, there's a 2 missing in there. Let's see if I can get that. I can't change that, but there should be a 2 right there. There's a mistake in the slide, 2s2. But this P is just 2 away from the nearest noble gas. So if oxygen gains 2 electrons to get a -2 charge, it will have a total of 10 electrons and a stable noble gas configuration of filled S and P subshell.